Okay, good morning, afternoon, or evening, everyone. Welcome to the first of a two-part SAR webinar, Introduction to Synthetic Aperture Radar, or SAR Earth Data webinar. This is your host, Jennifer Brennan. It is 2 p.m. Eastern Daylight Savings Time, so we're going to go ahead and get started here. First, what I'd like to do is go over a few webinar logistics. To ensure the best audio experience, participants have been placed in silent mode. But if you have any issues or you have any questions, what I'd like for you to do is enter those into the Q&A pod, and you'll find that located on the right-hand side of your screen. This works like a chat. Today's webinar is being recorded. The recording will be posted to our online Adobe Connect webinar catalog, as well as to our NASA Earth Data YouTube channel within a few days of completion. And once that's completed, I will send an email to all registrants with the recording links. As far as timing is concerned, today's webinar will be 1 hour long with 45 minutes allocated to the presentation and an additional 15 minutes for the question and answer period. Our speaker for today is Heidi Christensen. She is a GIS specialist at the Alaska Satellite Facility Distributed Active Archive Center, or ASF DAAC. After our speaker is finished with their presentation, we will move to a final optional set of polling questions. And generally, we give these questions about 3 to 4 minutes or so, and then we will transition directly to the Q&A following the polling period. Excuse me. Depending upon the volume of questions that are received, we will extend the Q&A period an additional 15 minutes from end time for those of you who wish to stay on the line with a hard cutoff of 3:15 p.m. Eastern Time. So now I've pulled up today's agenda. Heidi will begin today's webinar with an introduction to the key concepts of SAR data and the ways to use these data. From there, we will transition to an overview of data sets that are available at ASF DAAC, with a brief focus on Sentinel-1 data. And then finally, we will wrap up today's webinar by speaking to many of the SAR data resources, the data services, and the data tools that are available through the ASF DAAC. During today's Q&A session, just a final note, we will try to answer as many questions as possible. To maximize our time during the Q&A, our speaker will address those questions that may require a more in-depth follow-up offline. With that, it is my pleasure to introduce today's speaker, Heidi Christensen. Heidi, and I'm going to go ahead and pull up her slides. Go ahead and get started. Thank you, Heidi.
Okay, so you can hear me okay with the speaker?
I sure can. Thank you.
Okay, great. Welcome, everyone. Thanks so much for joining us. As Jennifer mentioned, thank you for the introduction. I will be going over some basics of the SAR datasets in this first webinar, and then on Thursday we'll look more at the practical applications of SAR. I work for the Alaska Satellite Facility. We are one of 12 distributed active archive centers that are spread across the country, and we provide data and support services for the Earth Observing System Data and Information System. Each of the DAACs has their own specialty in terms of the type of data that they serve, and ASF specializes in synthetic aperture radar data. We maintain NASA's archive of SAR data, which includes both data that has been collected directly by NASA, but also data sets that are collected by partner agencies, such as the European Space Agency, the Japan Aerospace Exploration Agency, and the Canadian Space Agency. We serve data sets that are easy to access and free to use. I'd like to go over some of the key concepts of synthetic aperture radar data acquisition. First of all, SAR makes use of the microwave range of the electromagnetic spectrum. So these have longer wavelengths than infrared, but they're shorter than radio waves. Secondly, SAR makes use of an active imaging system. So there's a very controlled radar pulse that is sent out from the sensor, and only the returns of those controlled signals are what's measured when they return to the sensor. And lastly, SAR makes use of a side-looking geometry. In order to process the data, it needs to be collected looking obliquely at the Earth. And while this is necessary, it also means that there are some distortions that are inherent to SAR datasets because of that side-looking geometry. So this is going to be particularly pronounced in areas with a lot of terrain or areas with lots of steep mountains. The benefits of SAR is that it can penetrate cloud cover. This is particularly important during natural disasters, such as a hurricane or a wildfire, where there's a thick cover of cloud or smoke, and you want to be imaging the Earth's surface beneath that, where many other sensors can't penetrate through the cloud cover. SAR can see through most cloud and smoke cover. So again, this is very conducive to mapping the Earth's surface during a natural disaster, or also in areas that are prone to frequent cloud cover, such as equatorial regions or western Alaska, where you have very few cloud-free days, which makes it really difficult to have a time series of data collected with optical sensors or some of the other sensors that are more sensitive to clouds. SAR is not sensitive to light availability because it's sending out its own active signal. It does not rely on the light of the sun at all for the signal. And because of that, it can collect data 24 hours a day, regardless of whether the sun is shining on that particular part of the Earth. With the addition of SAR sensors to satellites, there are now global coverage for SAR datasets. And many of the new constellations have really frequent and regular imaging cycles. So there are frequent return rates and very stable orbits, which allow for a really consistent time series data set that's being collected from the same place in space over and over on a fairly frequent basis. SAR can make use of different polarizations, which detect different aspects of the Earth's surface. So there are single pole sensor arrays that can only send out in one polarization and receive the signal in that same polarization. So if the waves are sent out vertically polarized, only the waves that return still in vertical polarization are measured, and that gives you the VV returns. Conversely, you could be sending out the signal in a horizontal polarization and only receiving in horizontal, which is an HH polarization. There are also dual pole sensors, which they still only send out in one polarization, but can receive in both that same polarization and the opposite. So if it's being sent out in vertical polarization, it can receive returns both in the vertical and horizontal polarizations, which are your VV and your VH returns. Also, you could be sending out in horizontal, receiving in horizontal and vertical, so you can get HH and HV. And lastly, there are quad pole configurations for a SAR sensor. And in that case, it can send out both in vertical and horizontal and receive in both vertical and horizontal, which gives you the full complement of polarizations, VV, VH, HV, and HH. Having all four polarizations can tell you a lot about what's happening on the surface. So it's a very powerful data set, but unfortunately, it's also very expensive and time-consuming to collect. It takes a lot of, there's just a lot of data that needs to be collected, processed, transferred, and so there are not a whole lot of full quad pole data sets. Lastly, SAR is sensitive to very small changes in elevation on the Earth's surface, which makes it an excellent tool for tracking changes that are caused either by geologic events such as earthquakes or volcanoes, or anything else that changes elevations or the crustal formation of the Earth's surface. There are two components of the SAR dataset. The first is amplitude and the second is phase. Amplitude is the amount of signal that is returned to the sensor, also called radar backscatter. So if a controlled radar pulse is sent down to the Earth, it bounces off scatterers, and some of that signal will return to the sensor. And that is what is measured as the radar backscatter. Backscatter is impacted both by the physical and the dielectric properties of the objects that are scattering the signal. And polarization interacts differently with different physical structures. So for example, the VV polarization is very sensitive to surface roughness. So if there's a very smooth, flat surface, it's more likely that the signal will just bounce off rather than, there will be less returns coming back to the sensor. Whereas if it's rough, there's a greater chance that some of those returns are going to be sent back to the sensor. So surfaces that are rougher tend to have higher backscatter return than surfaces that are flat or smooth. The VH polarization is particularly sensitive to volume scatterers, such as vegetation. So if the signal is sent out in a vertical polarization, but it interacts with the volume of the forest where it's being bounced all over the place, and the polarization can be changed from vertical into horizontal. And so if you're getting horizontal returns back from a vertical send, often that indicates that there's a volume scatterer such as vegetation present on the Earth's surface. The dielectric constant is also important in terms of how much backscatter returns to the sensor. The dielectric properties are basically the permittivity of an object to the radiation. So targets with a higher dielectric constant are more likely to reflect the signal, whereas objects with a low dielectric constant absorb more of the signal. So the returns will be higher from targets with higher dielectric properties than those with lower dielectric properties. If we look at the images on the right side of the slide, these were collected with the Sentinel-1 platform, which I'll be talking about more later. They were collected over the North Slope of Alaska, which is a very flat area with lots and lots of lakes. And it can be very windy at times. So if you look at the image in the top left corner, that is the VV returns on a calm day. And you can see that the water is very, very dark. There are very few returns coming back to the sensor from the water surfaces. And this is because on a calm day, the surface of the lakes are very flat and smooth, and water has a high dielectric constant. So the signals that are coming down from the sensor are basically bouncing right off of that surface, off in the opposite direction of the sensor, and very little, if any, of that backscatter is actually being sent back to the sensor. If you look at the image on the top right, which are the VV returns on a windy day, you can notice that there's a distinct difference. And this is because the water is instead of being a smooth reflector, it's now rough. And some of those waves may be facing the correct direction to be sending the signal back to the sensor. And so on those rough water days, you're going to see higher backscatter returns from the water than you would on a calm day. If we look at the bottom two images, those are the VH returns, and you can see that there is less impact of the wind for these products. So even though the surface of the water has become rough, it's still a surface scatterer. It hasn't generally become a volume scatterer. So if you have waves that are coming down in vertical polarization, anything that bounces back off the lake is still going to be in vertical polarization for the most part. So you'll have very few horizontally polarized returns coming from the lake surface. So on windy days, it can sometimes make sense to use the VH instead of the VV if you're trying to identify water surfaces. The last thing to be aware of when working with SAR data is that the wavelength of the sensor matters. And there are different wavelengths that are used for SAR sensors. Common wavelengths are C-band and L-band, especially for these large agency-run satellites. There are a range of other bands as well that are used for specific other applications. But for C-band and L-band, there's a big difference between 5 to 6 centimeters in the C-band and 25 centimeters in the L-band. If you were to send a signal down in C-band and there was a really thick forest that had deciduous trees with really big leaves, that 5 centimeter wavelength would not likely be able to penetrate very far into that canopy before it gets scattered back. And so most of the returns that you will be getting from a C-band sensor are going to be from fairly high in the canopy, whereas an L-band sensor has a much longer wavelength, and it can potentially travel kind of in between and around leaves and branches and reach farther down into the canopy. And depending on the forest, it may even be able to reach the forest floor. So the backscatter is going to be indicative of the conditions further down in the forest, either lower in the canopy or potentially even the dynamics of the forest floor. Similarly, in non-vegetated areas, the C-band sensor will not penetrate as deeply into the soil. So the returns you're getting from an open field, for example, are going to be from pretty high in the soil layer. So the surface of the soil is going to be what's indicated, and the conditions of that surface soil are what's going to be indicated by those returns. Whereas the L-band sensor can penetrate much more deeply and give you information about the conditions at a greater depth than the C-band sensor. So this is really important to be aware of if you're working with a SAR dataset, to understand which band is being used, because it will help you interpret the image. And also, if you're comparing data, if you want to look at historic data sets and compare with modern data sets, it's important to choose sensors that are collecting in the similar wavelengths. Otherwise, it's not an equal comparison. In order to make amplitude data useful for most cases, it needs to be radiometrically terrain corrected. As I mentioned, that side-looking geometry of SAR acquisition means that there are going to be significant distortions, especially in mountainous areas. If you look at the image on the left side of the slide, you can see that the mountains outside of Juneau, Alaska, they all look like they're kind of squashed over to the left with a really bright leading edge. If you were to overlay that with other imagery, it wouldn't match up at all. The mountains are in the wrong place, and you can't really compare the data that's being collected by the SAR sensor with your other layers. So this tendency to have the mountain squashed over are because if the slope of the mountain is perpendicular to the incoming wave, it can potentially be returning a signal from a large area of the slope all at the same time. So the sensor is interpreting all of that backscatter as coming from the same place on Earth, when really it's from a large area of the slope. And so not only are the mountain tops interpreted as being closer to the sensor than they really are, but their radiometric returns are also really concentrated, so it makes it look brighter than it truly is if it was spread out over the entire area that is actually being sensed by the signal. So in radiometric terrain correction, or RTC processing, we use a digital elevation model to adjust for these distortions. So basically, the pixels of the tops of the mountains are moved over into place based on the digital elevation model, so that they are terrain corrected, and then also the radiometric returns are spread out over the appropriate area that is actually being represented by those returns. And once that is done, then you have an image more like on the right, where the mountains are in place, the radiometric returns have been normalized, and you can now compare that data set with other images or use it to process or look at, compare, contrast, or augment other data sets. The other component of SAR data is the phase information. And the phase is the location of the wave along its cycle when it returns to the sensor. So the sensor sends out a controlled pulse, it travels down to the Earth, it scatters and comes back, and the wave is at a certain part of its cycle when it returns to the sensor. And the sensor can detect where it is in the phase. And if you were to come around the Earth again 12 days later on your orbit and take another image from the exact same spot, you send that signal down, it returns, it should be in the exact same place of its wave cycle when it returns that second time if nothing has changed on the Earth's surface. If, however, it is at a different point in its wave cycle, that indicates that there's a change in the distance between the sensor and the scatterer on the Earth's surface. And by comparing differences in phase, you can detect changes that have occurred in the Earth's surface. And this is the foundation of interferometry, where you're comparing phases from different acquisition dates to find regions that have been impacted by deformation or movement or anything that is going to change the elevation. And you can generate interferograms. So in this image on the right, you can see that there are a lot of fringes. And the distance between the fringes indicate how much deformation occurred. So if the fringes are very close together, that's a region that had a large amount of deformation. So you'll often see that right along a fault or kind of the epicenter of an earthquake. And farther away from the area of deformation, the fringes get farther apart. And as the fringes are farther apart, that indicates less deformation in those regions. And you can do additional processing as well to determine the actual quantity of deformation. To access SAR data, you can use ASF's Vertex data search portal. ASF offers a lot of different data sets. I'll go through some of them in the next few slides. But it's a large amount of data that's all free to access and available to the public everywhere to use. In order to download data from ASF, you need to have an Earth Data login credential. This is the EOSDIS user registration that applies across the DAACs. And so all you need is one Earth Data login, and you can access a lot of different data sets. So if you don't already have Earth Data login credentials, you can visit the urs.earthdata.nasa.gov site and sign up to get your credentials. It's free. It's just a simple form to fill out. There is also a link, if you notice on the right side of your Adobe Connect screen, there's a link that has, there is a pod that has a list of links, and that includes the NASA Earth Data login link as well, if you want to use that. Once you have your Earth Data login credentials, you can then sign into Vertex. So there's a sign-in button, and this is where you would enter your Earth Data credentials when you visit our search.asf.alaska.edu site. Once you've logged in, the first time you log in, you'll be prompted to accept the ASF end-user license agreement. And once you've done that, you will have access to almost all of the data sets that we have available, and you can download them, whichever ones you want. ASF hosts a number of historic data sets. So these are missions that are no longer active, but we still maintain that archive of data. And so you can access these older data sets, which is particularly useful if you want to do comparisons through time. We have quite a range of data sets going back to the very first spaceborne SAR mission, which was a NASA mission in 1978 called CSAT. And then we have a number of other data sets available from a number of other partner agencies. Most of them, as I said, are just free and available to download, but we do have a couple of data sets, the JURS and RADARSAT-1 data sets, that do require an additional research agreement. So if you want to download these data sets, you'll need to fill out a form to ask for permission to use those data sets. But otherwise, everything is freely available. You just need to log in and you'll be able to download. We also support a number of ongoing missions. One of them is UAV SAR, which is actually an airborne mission. So the SAR sensor, it's an L-band sensor that's mounted on an aircraft. And so the data sets from the UAV SAR missions are much higher resolution, but they're also much smaller footprint. They tend to be very specific mission-oriented flights. And if you look at the image up in the right corner, you can see that's the UAV SAR coverage in Alaska. And it's quite patchy, and it's patchy both spatially and temporally. There are often not frequent reflights depending on the nature of the mission. But if one of these flights happens to be over your area of interest or at the time that you're interested in, it is a really rich data set, and there are a lot of higher level products, and the products available can vary from mission to mission depending on the goal of the mission. But it's a very rich data source if it happens to coincide with your area of interest. Another ongoing mission is the Soil Moisture Active Passive mission, which is a NASA mission that originally had both an active and a passive microwave sensor. So unfortunately, the active sensor, the SAR sensor, failed after about 3 months after launch. And so for those first 3 months, we have that data set available to download, but since then, it's just been the passive sensor, which is still actively collecting data. And there are a lot of soil moisture products that are available from SMAP. And if you're interested in that, it is, with the loss of the active sensor, we lost the high resolution aspect The goal originally was to have high-resolution soil moisture data for the whole world. But now it's just soil moisture data at a much coarser resolution. But if you're interested in regional dynamics or continental scale or country scale dynamics, this is a really rich data source that you can check out. If you visit the SMAP website at JPL, they have links to both the data sets that are served by ASF and then also most of the passive sensor data sets are served by the NSIDC DAAC. The largest data set that we have and the most frequently accessed is the Sentinel-1 data set, which is part of the European Space Agency's Copernicus mission. This mission gives global coverage with C-band SAR using a constellation of 2 satellites. The first satellite was launched in 2014 and the second in 2016. And the cool thing is that while each satellite has a 12-day repeat cycle, they're offset from each other on the exact same orbit by 6 days. And so there is collection from the same place in space over the same piece of Earth pretty much every 6 days between the 2 satellites. If you live in the polar regions like I do, it can be much more frequent coverage actually because these are polar orbiting satellites, and so the paths often overlap quite a lot at the top and bottom of the Earth. And so you can get some areas that get very frequent coverage. New data is available to download within 3 days of acquisition, and generally, actually, it's available within 24 hours. So as soon as ESA finishes processing the data, we ingest it and make it available on our website for people to download. Sentinel data is free and easy to download in several formats. And I'd like to go over some of these different formats because it can be hard to know which data set is appropriate for use in your particular application. If you were to search for Sentinel-1 on ASF's Vertex data search portal, you would get returns for raw data sets. And in general, there is very little use in the raw data sets for most SAR users. The raw data sets are really for SAR experts who want to take their processing chain through the entire way from the raw data to their finished product. But for most SAR users, the level 1 products that are generated by ESA are going to be what you're most interested in. ESA generates GRDs, which are ground range detected, and SLCs, which are single look complex level 1 data sets. The GRDs are best to use if you are just interested in amplitude data. They no longer contain the phase information, which is still available in the SLCs, but they've been multi-looked into one single geotiff, so all you need to do is bring in a single geotiff for each polarization. You can bring it into your GIS directly. There still is the terrain problems and the distortions that need to be corrected, but otherwise, you can bring it into your GIS. It'll line up with your other data sets. It's a much smaller file than the SLC and perfectly appropriate if you want to generate RTC images, for example. If we look at the SLC product, you can see that it contains a lot more stuff. So each of the SAR images are actually made up of subswaths, and there are 3 subswaths in this image here. So 1, 2, 3. And then within each one of these subswaths, there are individual radar bursts. And if you were to bring this image into your GIS, the corners would all be in the right place. But if you look above and below each one of these demarcation lines, you would see that the data is duplicated. Each burst actually overlaps the next burst, and all of that data is displayed in this image. And so everything inside the 4 corners is going to be kind of squashed together to accommodate that extra information. So this, if you just want to bring an image into a GIS or look at it, visualize it, see if it's something useful, you're better off looking at the GRD than the SLC. Also, the SLCs are still in their subswath. They are delivered in 3 different geotiffs. So each one of the subswaths has its own file, whereas the GRD has all been multi-looked into one single geotiff. If, however, you are wanting to do interferometry, you must use the SLC. As I mentioned, it still retains the phase data, which the GRD does not. And so if you want to generate interferograms, you'll need to download the SLC. Looking for the future, we're really excited about the NISAR mission, which is due to launch in 2022. This is a joint venture between NASA and the Indian Space Research Organization. And the sensor will have, their satellite will have an L-band sensor and also an S-band sensor, which is used more for atmospheric applications. But the L-band sensor will be on a 12-day average repeat cycle, which is similar to Sentinel-1. And so we're really excited to have both L-band and C-band being collected regularly on a similar schedule. So it will really expand the opportunities for comparing those different wavelengths. The other really exciting part is that part of the mission is to provide analysis-ready data products. So for NISAR data, you will not need to do any additional processing to get an RTC or an INSAR product. Those will already be generated for you. And so you should be able to just visit ASF's download portal, find the things you want, and carry on. And they're all ready to bring into your project and start working with them. So we're really excited about having that accessibility for SAR users. ASF has a number of resources and tools available to help you work with SAR data, and I will go through each one of these individually with their own slide. First of all, as I mentioned, we have our Vertex data search portal. If you've visited Vertex in the past but haven't been there for a while, you'll notice that it looks really different. It underwent a complete overhaul about a year ago, and so the interface is quite different. Even since that time, there have been a lot of updates and features, new things that have been added. And if you haven't been there for a while, I encourage you to check out the What's New button, which is up in the right-hand corner. And that gives you a list of some of the new things that have been introduced since the overhaul. I'll go through a few of the new features, which include the baseline tool. If any of you have used the baseline tool in the past, you will find that it's now been more fully integrated into Vertex, and some upgrades have been made. I'll actually do a separate slide on that next. It's a pretty exciting new feature. Another component is that you can now view the contents of some of our zip archives and download them individually. So for some data sets, well, for many of our data sets, we actually distribute them in zip files. And it can be hard to know what actually is all included in the zip file. And for some of our data sets, you can now just expand those zip files and see what all is contained. And if you just wanted one small file out of there and it's smaller than the zip file entirely, you could just choose to download that separately rather than downloading the entire zip file. So that's exciting. Another new component that is available is through your Earth data login, actually. If you've logged in, you can save your searches, and also it keeps track of your search history. So if you've been looking around and you had one great search that you weren't sure of, and you were looking at a different path and decided that actually you prefer that original path, you can go back to your history and find that search that you did and bring that up instead. Or if there's an area that you search over often and you want to save your search, or you're looking for data sets and you think that this is a pretty good search but want to check out some other things, you can actually name your search and save it specifically in your profile. And so you can go back and look at that same search. The other component of the new Vertex is that it's very easy to share your searches, because everything that is required to search is contained in the URL. So all you have to do is copy that URL. If you're collaborating with somebody, you could send them that URL, they paste it into their browser, and it'll give them the exact same results that you're looking at. So that's a really convenient feature. So the baseline tool is designed to help you choose appropriate pairs for doing interferometry. So if you have a reference granule that you know you want to compare to something else to make an interferogram, you can now enter that directly into Vertex. So in the Vertex platform, there are a couple of search type options. There's the geographic search where you can draw in your area of interest and search for data sets that occur there. Or there's also the list option where if you have a list of granules that you're interested in, you can paste that in and it'll bring up all of those granules. And now there is a new search type, which is called baseline. And if you know the reference granule that you want to use, you can type it in or paste that in, click search, and it will open up the baseline interface directly within Vertex. Another option is if you're just searching for SLCs, you can see that there's a baseline tool button that's included with each one of those data sets. And if you find an SLC that you're interested in creating an interferogram with, you can select that tool and it will take you to this same interface. Now, basically, the baseline is the distance apart. So there are two different baselines, actually. There's the perpendicular baseline, which is shown on the y-axis, and the temporal baseline, which is on the x-axis. So in order for granules to be used to create an interferogram, they have to have been collected from close enough together in space that they're coherent. So there is a critical baseline that must be met. They have to have been acquired within that range of each other. So the baseline tool only will select granules that fall within that critical baseline, or the perpendicular baseline. But you also want to consider the temporal baseline. And the appropriate temporal baseline, or how far apart the two granules are in time, is going to depend on your particular application. If you're interested in looking at the deformation caused by a really discrete event like an earthquake or a volcano, you generally want to have an image that is collected as soon before the event and as soon after the event as possible, so that most of the change you're seeing can be attributed to that specific event. So in that case, you'd want to have the granules be as close together as possible in time, as long as they bracket that event. On the other hand, you may have slow processes like a subsidence of a groundwater area that's causing the ground to very, very slowly sink in. And in that case, you may just want an annual interferogram where you look at the change that has occurred on the same date from one year to the next. And in that case, you would want an annual interferogram. So the temporal baseline is going to differ based on your application. The important thing to remember is that you want to be able to find the impact of that event that you're interested in and not have it clouded by other things. So if you're interested in an earthquake effect and you take granules that are 3 months apart, there's a chance that there are other things that have happened, like the vegetation may have changed, or other things may have occurred, or construction, or other things that can change the elevation of the Earth. And so you can be muddying your signal from that earthquake if you have too long of an interval. We do have a few different analysis-ready products that are available for download directly from Vertex without any additional processing. We hold a subset of the ALOS Pulsar 1 imagery, and this was a mission of JAXA, the Japan Aerospace Exploration Agency, and for all of the holdings that we have for the Pulsar 1 mission, we've also generated RTC products. So from the data set in Vertex, you would just select the ALOS Pulsar mission, and then under the More button for the additional filters, you can select the file type and select one of the two terrain-corrected products. The high-resolution terrain-corrected products are 12.5 meter resolution, and the low-res are 30 meter. They're projected to UTM coordinates. You download them, you can bring them into a GIS. They're ready to use right away without any additional processing. We also have a small collection of Sentinel-1 interferograms that can be downloaded directly from Vertex. So these have already been processed to interferograms. And similar to the PelSAR mission, you would just select the S1 InSAR beta option from the dataset selection and enter your area of interest and any additional search parameters, and you're ready to go. So while they are over a limited area on Earth, they tend to be over geologically interesting areas. So it may coincide with one of your areas of interest. Or if you're just wanting to find out what interferograms are and how they behave and the difference between them, you can just go and explore this data set because you don't have to do any processing. They're ready to download, and you can explore and take a look at how you would potentially use interferograms. We provide a number of data recipes, which are step-by-step tutorials that walk you through SAR processing. And there are quite a wide variety of topics, including radiometric terrain correction using a variety of different approaches, InSAR, inundation mapping, environmental change detection, and if there's a recipe that you think should be there and isn't, let us know and we can look into the possibility of generating one that addresses your particular application. And lastly, we have our HYPE on-demand SAR processing platform. This is something that we use internally to process SAR data. Because SAR is such a large data set, and it requires often a lot of memory and processing power to do higher level processing of SAR, cloud computing is a really excellent solution for dealing with these large data sets that you don't always need that much computing power, but when you need it, you need it. So we have our on-demand cloud processing system, and you're welcome to give that a try and process your own products using this platform as long as you provide us feedback. So if you're interested in trying this out, you can visit the HYPE website. Again, all of these websites are listed in the links pod on the right side of your Adobe Connect screen. So you can visit our website, request access to the HYPE platform, and in exchange for feedback, you get a quota of a certain number of jobs that you can process each month. And we have RTC, InSAR, change detection, and just a number of different processes that you can try. And it's a great way to get products in your particular area of interest without having to process them yourself. So with that, I'm going to turn it back over to Jennifer.
Okay, thanks everybody. At this point, we are going to move to the optional polling questions, and we'll give these about 3 to 4 minutes or so, and then from there we'll move directly to the Q&A period. So no worries, all of your questions are still within the Q&A pod. We'll get to as many as we can. Any questions that really require some in-depth feedback are questions that our speaker will follow up with you offline. So thanks so much. Let's give these a few minutes, and then we'll transition to Q&A. Okay. At this point, let's go ahead and move to the Q&A session. And we had quite a few questions. If you could bear with me for just a moment here, you'll see that there is contact information to the left. Our speaker's email address has been provided as well. Just give me just a second here and I will find our first question. Okay, everybody. Just a couple of words about our webinars here. The webinar on Thursday is also full. However, what I will try to do is provide guest access information, a few minutes after start time for just in case all of our registrants, that we have not filled up the room. So our first question is, do you know how I can access Sentinel-1B data?
So both of the Sentinel-1 platforms are available on ASF. We don't really treat them differently. So if you want, you can select in the more filters or in the additional filters, you can select specifically one platform or the other. But generally, we don't distinguish between 1A and 1B in terms of the collection. So if you select Sentinel-1, you will see all of A and B.
Okay, thank you, Heidi. The next question is, where LiDAR is being used to map forest floor features, would SAR at larger wavelengths be a cheaper but just as effective alternative to create DEMS, locate under canopy features, etc.?
So LiDAR and SAR can be complementary. If you've done a really nice digital elevation model with your LiDAR, and then you compare it to the SAR dataset and see how it compares, if you can find a good correlation, then you could use your SAR data for kind of more frequent observations to fill in those blanks in between visits with your LiDAR, because it certainly is a lot less expensive. But LiDAR gives you a lot more information, a lot finer grain, and so you need to probably, in most cases, you'd want to sort of compare that initial data set of LiDAR with your SAR data so that you can find out if it is a useful tool, because a lot of it will depend on your site.
Okay, great. Thank you, Heidi. Could you provide a basic introduction to, or define interferometry? That's a mouthful right now. Please. It's
hard to get basic with interferometry, to be honest. And so it would probably be better to reach out to us directly, and we can provide information specific to what you're actually interested in. But at a very basic level, it's looking at the differences in phase. So you look at the coherence between the two phases, and if it's coherent, then you can determine the differences between the phase measurements. So places that are incoherent, for example, places with a lot of vegetation, they can really change rapidly, and it may not have anything to do with the underlying ground. So if you're trying to use interferograms in like a heavily forested area, it may not be a valid application, just because there's so much else going on that's going to muddy your signal, and you won't be able to tell what is being driven by actual crustal changes and what's being driven by the vegetation. But I'm not sure how much more. Yeah, it's hard to be basic and yet informative. So if you want to get in touch, we can address your specific questions more appropriately.
Well, that sounds great. Thank you, Heidi. The next question is, what is the earliest data set that's available through ASF?
Our oldest data set is from 1978, and that's the CSAT mission. And then there's a pretty big gap, actually, between that and our next one. But we have a lot of data sets kind of starting in mid-2000s. So with the PAL-SAR mission, that was a big game changer. And the GRD and ERS missions, so early to mid-90s, had kind of one pulse with SLC, which there's not very much available yet for that. But for GRD and ERS, those are kind of the early data sets from the 90s. But then once you get into the mid-2000s, there's quite a lot of data. It's not until Sentinel really, in terms of our data sets, that we got such frequent coverage. So even the PAL-SAR data, you're looking at more like a month interval between the data sets, between the acquisitions, whereas Sentinel, it's more like a week. So that was a significant change in terms of putting together a time series when Sentinel was launched.
Okay, thank you, Heidi. So the next question is, if you want to do deformation mapping, what Sentinel data product should you use?
So the deformation mapping, that comes back to interferometry. So basically, you would use an SLC, download your SLC, and then process to an interferogram, and then use the interferogram then to continue on and look at the actual deformation mapping and trying to determine the actual quantity of movement. And we have data recipes that walk you through that process as well. So I encourage you to check that out. But that's your first step, basically. You need the SLC products and then process for the phase information.
Thank you, Heidi. And I did provide a link into the Q&A pod that really has a chart that compares the various SAR data sets that are available through ASF. The next question is, what is the resolution of UAV SAR?
Oh, that's a good question. It will probably vary by mission. I would have to look it up. I'm not sure. The products can really vary with that mission, just because there were different goals for the different missions.
Okay. Thank you, Heidi. The next question is, I use Sentinel data often for post-disaster assessment. One of the main shortcomings is the performance of the images in hilly areas. They try to overestimate the flood extent. What is the best approach to deal with this?
So the most important thing to start is to make sure that you're using radiometrically terrain-corrected data. So that is going to help with the placement of the hills and help expose the actual inundated areas. So at the same time, there are limitations because it's not a super high resolution data set to begin with. There are some smaller creeks and things that you're not going to be able to see. They're going to be hidden from the SAR sensor, just because if that creek is kind of down in or the river is down in a steep canyon, for example, you may not be able to get any returns from that area. So it will depend on your particular application, and if you have questions and you want to send us a specific image as an example, then we can look at some of the different impacts that are driving your difficulties and maybe help work those out if it's possible to work them out. But certainly the first step is to make sure that you are working with a radiometrically terrain-corrected data set.
Okay, thank you, Heidi. The next question is, and I know that we did speak to the fact that the radar instrument on board SMAP failed within a couple of months of launch, but is it possible to use SMAP L-band for forest height estimation? I don't know if ASF DAAC has data sets currently that could be used for that purpose.
Yeah, that's an interesting question. I'd have to look into that, and in the next webinar, I'll be mentioning the SAR handbook, which has been developed to help with forest biomass estimation and those types of things. And if you just search for the SAR handbook, and it was put out as a joint project with Servir, which is capital SERVIR. If you search for the SAR handbook, you can find it's got really good information. So if you're interested in looking at biomass measurements, that's an excellent resource because it is focused on forest applications. But as for the particular application of SMAP, I'm not sure. I'd have to look into that more closely.
Okay, thank you, Heidi. So the next question is, are you indicating that the Sentinel-1 in Google Earth Engine is only for amplitude applications?
Sorry, could you repeat the first part of that question?
Sure. At a certain point, you were speaking to the Sentinel-1, and the question was, are you indicating that the Sentinel-1 in Google Earth Engine is only for amplitude applications?
Okay, so I'm not aware of any interferograms that have been loaded into Google Earth Engine, but things change all the time, so I might not be up to date. The only data sets that I have actually used on Google Earth Engine for Sentinel-1 have been terrain-corrected data sets, and that's a valuable resource. It's important to note that as of the last time I checked, they weren't radiometrically corrected. So if you're trying to use the radiometry, as long as you're being consistent and using the same data set, if you're looking for change, probably that's okay. But they are terrain corrected, but not necessarily radiometrically corrected. So it's important to read through the documentation and make sure that what you're looking at is what you think you're looking at.
Okay, thank you, Heidi. The next question is, will NISAR data be freely available?
The NISAR data, was that?
Yes.
Yes. So NISAR will be, that's a NASA data set, and so we will be putting it on our ASF Vertex data portal, and everybody can download and use it. It will be freely available to the public, including the higher level products.
Okay, wonderful. Thank you. The next question is it possible to use PALSAR L-band data to generate the canopy height of the coastal vegetation? Is this something we should?
Yeah, this is a pretty specific question. I would guess that the L-band is not going to be great for canopy height, just because the canopy it's not likely to be returning from high in the canopy because of the higher penetration of the L-band. It will depend on your particular data set, and so you can always try and compare it with ground truth known data and see how it performs. My guess is that L-band is probably not going to be great for that, but it's potentially worth a try. And if you get in touch, we can put you in touch with people who are working with that more directly.
Okay, thank you. And it might also be worth looking at the new data sets that are available from the JEDI mission as far as canopy height is concerned. We recently held a webinar on that topic, so I'm going to put the link in here to the JEDI site. I know that's a LiDAR instrument, but it might be worth checking that out. So let's see here. The next question is, I want to do an assessment of cyclone impact on the mangrove forest using SAR data. Which SAR, Sentinel-1 or ALOS PALSAR data would be most suitable?
So the data set that we serve for PALSAR is from just the first PALSAR mission. So PALSAR-2 is there is data for PALSAR-2, but we don't serve it through our site. We were not contracted to serve that data. So the only data that we have for PALSAR is older data. In terms of your application, I believe the question was Sentinel-1 versus the PALSAR, is that correct?
Yes.
So again, that's going to be largely driven by two things. First of all, the wavelengths are different. So the PALSAR is an L-band wavelength, and the Sentinel is a C-band wavelength. And so it would probably be a good idea to check against your ground truth data and see which one performs better. I am not sure of the repeat cycle of the second PALSAR mission. I'm not very familiar with the second PALSAR mission, I'll be honest. So I'm not sure what the repeat cycle is. Sentinel-1 has pretty regular coverage, so if you're looking for frequent returns, that may be a good choice as long as the C-band is appropriate. If you find that for the application you're interested in, you want to have higher penetration down, like if you want to see, like if things are flooded underneath the canopy, then an L-band sensor is probably going to be a better choice, but it will really depend on your specific site.
Okay, thank you, Heidi. The next question is, the processing of SAR SLC data using SNAP takes too much time and shows errors. Are there any other tools to process SAR SLC data?
Yes, so JPL has a free, like open source software called ICE. It's ISCE, and that is a very good tool for processing in SAR. If you want to create SLC, if you want to generate interferograms from SLCs, the ICE program is a good option. It is a little bit difficult to install, so that can be tricky. If you want, I would suggest checking out the HYPE platform. Visit our website and the hype.alaska.edu website and sign up for that, because if you're not able to install ICE successfully, that's going to be a hurdle. But in terms of software that's freely available, that's probably the next best option is ICE.
Okay, thank you, Heidi. Can you provide an explanation, describe the difference between a DEM and a DTM?
So DEM is sort of a generalized term, whereas especially once LiDAR came around, where you were getting, you could have digital terrain models and digital surface models. There's a difference between how far the signal can penetrate. So if you're getting returns from the surface, it's the first return from the LiDAR, for example, whereas the last return is when it hits the ground and comes back. And so in the old days, often there were a variety of methods used to generate DEMs, and it wasn't super explicit necessarily if you were looking at more the surface or more the actual terrain. Whereas now, with a lot of new approaches for generating digital elevation models, you have both a digital surface model and a digital terrain model, and those differ because the surface, and I don't deal with this very often, but as I recall, the surface is that first return. So you're looking at kind of the top layer of stuff that's on the Earth, whereas the terrain model is the actual bare Earth. So if you're interested in having if you could use a variety of things. If you're looking at the difference between, in canopy height, for example, that's where LiDAR is very helpful, because you're getting those first returns, or the surface, and then the terrain, and you can look at the difference between those and determine how much vegetation is there. So it's important to be aware now that there are so many options for DSMs versus DTMs, being aware of what it is you're using, whereas DEM is a more generic term. So what we use is when we are doing RTC, we use publicly available digital elevation models. So most of them are the shuttle radar topography mission. So I believe that was an L-band sensor. So in most cases, it's going to be the surface of the Earth, but there may be some cases where it's a little higher up in the canopy. But it really depends on which product you're using. And now that with so much LiDAR, it's important to be aware whether you're using the DSM or the DTM.
Okay, thank you, Heidi. All right, the next question is, and we've got about 4 minutes or so left for the extended Q&A. The next question is, all right, let's see here. Different polarizations like VH HV can occur due to different natural or man-made objects, how can we find which object generated the particular polarization in the study area?
That's a good question, because things can scatter off a number of things. The signal can come down, and what you're getting back is the sum of all of those vectors where it bounced around. So it may have hit a building and then hit a tree trunk and then hit some leaves, and all of those things together then are integrated into your return. So it can be difficult to pinpoint in that way what actually caused the change in polarization. That would be a question that I could pass along to our science team, and if someone has a more concrete answer. But it can be hard to pick out particular scatterers unless there is one scatterer that sort of overwhelms all the others. If there's a very bright building, for example, and you're getting HH returns, that building is likely going to overwhelm all the rest of the scatterers that are contributing to that signal that's being returned.
Okay, well, thank you, Heidi. The next question is, in areas of slopes or uneven topography, I have problems differentiating forest from scrub or grassland with Sentinel-1. Only areas without vegetation can be differentiated, which occurs when preparing the land for cultivation. Is there anything I can do to differentiate different covers in areas of uneven topography?
So that's interesting. Yeah, so trying to identify crops using only Sentinel-1 can be a little bit tricky, because different crops can have similar signals. So if there are certain types of crops that do have significantly different returns just because of the structure of the crop, like if it's rice at an early stage, you have mostly water, so the returns are really different than rice at a later stage, which is going to have more double bounce. But in terms of different crops, I'm not sure how you would necessarily differentiate solely using Sentinel-1. This may be a data fusion question where you would combine two data sets to so if the single signals from the SAR is not enough to differentiate between different crop types, and especially if you've done the RTC correction so that you're correcting for the differences in the slope. At that point, I'm not sure if it can be gleaned just from the Sentinel-1, and you may need to incorporate some other type of data set to be able to differentiate between those. But we'll check in with that question and send it along to people who know more about that than I do.
Sure, thank you, Heidi. So at this point, we have not answered all the questions. It is 3:15 p.m. Eastern Time. What I will do is I will leave the virtual meeting space open an additional 10 minutes or so. If anybody has any additional questions or notes that you would like to include, please add those into the Q&A pod. We will log off from the audio component, and we'll send the Q&A log to our speaker so she can follow up with you if your question has not been answered. Okay, and certainly feel free to email her directly, or you can email me and I can forward anything along to our Alaska satellite facility. I do want to draw your attention to the fact that the presentation file is available for download in the lower right-hand corner of your screen. This is the persistent feature. If you click on that file name, you should be prompted with an option to download the file. And with that, I'd like to thank today's speakers. If you have any additional questions about part 2, that'll take place on Thursday, and whether or not you are registered, please know that we will also hold an encore presentation on August 4th and August 6th. And I expect to have the registration information set up on our Earth Data website, earthdata.nasa.gov, within the next couple of days. And certainly feel free to email me with any questions. So thanks to all of you for joining us today, and thank you, Heidi. At this point, we will log off from the audio component. All right, thanks everybody. I hope to see you online on Thursday. Take care. Bye-bye.